Okay, picking up where we left off on the next page, we begin with defining a couple of terms, the point estimate and the margin of error. So it turns out we've already been doing these things in those previous examples. We just didn't refer to them with these names. So let me explain what's going on here. The point estimate is the mean of the sample data x bar. So we give a new name for the sample mean. Um, we now call it the point estimate when it comes to a confidence interval. Why is that? Well, remember the sample mean is you're always hoping to estimate your population mean. And so hence the word estimate. Why is it the point estimate? Because it's just a single value. So that's your very best guess at what the population mean would equal. You would say, well, if I had to guess one number, right, 1 point, then I would say it's the sample mean. However, we know that that's probably not the case, although the population mean is probably very close to it. That would be the one number that if we had to guess one single value, 1 point. Okay. Hence why we need a margin of error. So the margin of error, you have to see noted as ME, like in formulas. The margin of error is the difference between the sample mean and each boundary of the confidence interval. Okay, so the margin of error is what we found when we computed those distances. The distance from the mean to the upper bound and the distance from the mean to the lower bound. And you see that formula right there. The margin of error is found by this formula. ME equals Z sub alpha over 2 times sigma over the square root of n. I have the sub alpha over 2 there. You can really, most of you guys can probably just ignore that and just think of it as Z times sigma over square root of n. If you think you might be taking more statistics in the future, then I'm going to explain super, super briefly what that sub alpha over 2 comes from. And finally, you see there at the bottom, the confidence interval is x bar minus the margin of error, comma, x bar plus the margin of error. Well, that's what we did to find the lower bound and the upper bound, which define our confidence interval. We take the mean and subtract the distance, and we take the mean and add the distance. Okay, so it's like your point estimate minus your margin of error and your point estimate plus your margin of error. So I want to recap those things here and just connect them to our previous example where we found the 95 and 99% confidence intervals. So we had a sample mean of 54, so that was our point estimate. Our point estimate was equal to 54 in those examples. In part A, remember we found the distance to be 1.66, so that was our margin of error. Margin of error equaled 1.66. In part B, our margin of error equaled 2.19 with the 99% confidence interval. And now let me explain just very briefly what's happening in this formula. I'm always going to refer to this formula as simply Z times sigma over the square root of n, and we know it's the Z-score for the upper boundary, right? But just where does that? Maybe some of you guys are going to take statistics in the future, and you're going to see this again, and so I want you to be aware of what's going on. Let's take, for example, the 95% confidence interval. If we look at the 95% confidence interval, then the alpha that would go with that is 5%. Okay, the alpha is always the what's left over. So if we've got 95% confidence, the alpha is like the uncertainty, right? How much else is there? 5%. Or you might say alpha equals 0.05. Same thing, right? So why would this be alpha over 2? Well, let's take a look. What would be alpha over 2 in this case? Well, take that 0.05 and divide it by 2. 0.025. Z sub 0.025. And if you remember what Z sub alpha means back from in chapter 6, that alpha is the probability above a certain Z score. So it's like you're trying to find the Z score that has a probability of 0.025 above it. And it turns out that this one with 0.025 would equal a Z-score of 1.96. The Z-score with 0.025 area above. Right? So why would that be the case? Just to really connect the dots, if we go back here, if we were to think about the 95% confidence interval, right? 95% in the middle. Well, then how much is in each tail? 2.5%, 2.5%. So if we wanted to know the Z-score here, that's the Z-score with 0.025 above it. And it turns out, and we just used the StatCrunch calculator, right? That Z-score there with 0.025 probability above is Z equals 1.96, which is what the StatCrunch calculator told us. We could, of course, use the Z table and do it that way. That's what we did in chapter 6. Okay. Just for those of you who might go further with statistics in the future. Okay, let's jump into practice number 2. It says a survey of 30 adults found that the mean age of a person's primary vehicle is 5.6 years. Assume the population standard deviation is 0.8 years. Okay, so part A, what is the point estimate of the population mean? Right, well, remember what point estimate is? It's the sample mean, right? So what is our point estimate for this problem here? A survey of 30 adults found that the mean age of a person's primary vehicle is 5.6 years. Population standard deviation is 0.8 years. Well, there's no work to do here. The point estimate is X bar, and they tell us that is 5.6. We remember that it's a sample mean. Okay. Part B, now we're going to do a confidence interval. Find the 90% confidence interval of the population mean, which will round to 2 decimal places. So you'll notice as you do more of these problems, there's a few confidence intervals that are by far the most popular. The most popular easily is the 95% confidence interval. And then slightly less popular than that is the 99% confidence interval and the 90% confidence interval. We really see those three the most. You could do a confidence interval with any percentage, but the 95 is by far the most popular, and then after that the 99 and the 90. Okay, so we get to try out a 90% confidence interval here. We need to know that population mean. Okay, so at this point we'll go to our normal calculator. Be sure you are using the between version. And so in StatCrunch, in your normal calculator, with the between, you'll see those 2 blanks, and you're going to fill in this part over here. The 90%, we put in 0.90, hit compute, and you notice I say this should really be a Z. I explained that earlier though. Okay, when we go backwards from the 90% confidence interval, we get the numbers negative 1.6449 and positive 1.6449. All right. So that is our Z, which we'll put into our formula. margin of error is equal to 1.6449 times, and there's our standard deviation of 0.8, divided by the square root of the sample size, which in this case was 30. So multiplying those all out and rounding to 2 decimal places, you get 0.24. Okay, once we have the margin of error, remember this is how we do our confidence interval. We take our point estimate and we subtract that margin of error for the lower bound. Take your point estimate, add that margin of error for the upper bound. And so 5.6 minus 0.24, comma 5.6 plus 0.24 gives us this 5.36, comma 5.84. We are 90% confident that the actual population mean falls between these two numbers. A little bit less and a little bit more than 5.6, like that. Okay, very nice. So really we're doing one more example of finding a confidence interval here. Now the 90%, but now we're using that language of the point estimate and the margin of error. Very nice. Let's go ahead and check out number 3. Now we're going to start to mix things up a little bit. It says a researcher wants to know the mean IQ score for the population of first-year college students. What's the average IQ score for first-year college students? Okay. Assume the population standard deviation is 15 IQ points. How many first-year students must be randomly selected if the researcher wants 95% confidence that the sample mean is within 3 IQ points of the population mean of all first-year college students? Okay, wow. A lot happening there. So you notice we're told what confidence interval we're taking, right? We want the 95% confidence interval. But then we're told we want to know that the sample mean is within 3 IQ points of the population mean. And then you're like, what are they even asking us to find? Way back at the beginning of that sentence, how many first-year students? It's the sample. How big should the sample be? That's what we're trying to figure out. Now, this is really cool and very, very applicable and how statisticians use this idea out in the field. They know they want, let's say, to be 95% confident, but they also want to be within a certain distance from the sample mean. They've already got that in their head. I want to be 3 IQ points away at most from the population mean. 95% confident, right? So how big of a sample size should I take? And so you kind of do this even before you begin, your research, so you know already how big of a sample size you want. Okay, so here's the idea. We're still going to use our formula, right? Margin of error equals z times sigma over the square root of n. But it's n that we're going to be looking for. We're going to know sigma to plug in. We're going to figure out the z-score to plug in. We're even going to know the margin of error to plug in. And then we can solve for n. Okay, well, some of these we know already. Let's just kind of go over here. So n is what we're looking for. We know sigma is 15. Okay. Oh. Car is driving by. All right. So we know sigma is 15. Because we're using a 95% confidence, we could go and use our normal calculator in reverse to find the z-score. It's going to be 1.96. So with 95% confidence, this is kind of something nice about confidence intervals. If you're doing a 95% confidence interval, that's always going to have a z-score of 1.96. So it might be something that you just remember. 95% confidence, that means the z-score 1.96. It's never going to change, which is something really nice about the normal distribution. If you forget these, or if you don't want to remember them, you can always use the normal calculator in StatCrunch backwards, right? Put in 0.95 and hit compute, and it will tell you negative 1.96 and positive 1.96. But it's always going to be that. It's not going to change. And on that note, now that we've done the 95, the 99, and the 90, these are the z-scores that go with each of them. So with 95%, well, okay, we just set it, z equals 1.96. For the 99, remember our z-score was 2.5758. And the 90 that we did just a second ago, z equaled 1.6449. So you're going to be using these confidence intervals, and so these z-scores quite frequently. And so some students choose to just remember them. But if you were to remember just one, remember the 95%. And of course, you could find them all in the calculator as well. Okay, so I'm not going to show the work here because that would be using the calculator backwards, or you could just know it's 1.96, so that's what we'll plug in for z. We know sigma, we know z. What about margin of error? Okay, this is interesting. What's the margin of error in this example? And maybe you're looking, well, there's only one number left. The margin of error is the 3. How is it that the margin of error is the 3? So notice how that's phrased. We want the sample mean to be within 3 IQ points of the population mean. So the distance should be within 3. And so our margin of error, how far do we go in both directions, is the 3. And that word within that comes before it really tips us off. Okay. Well, now that we know all these values and we have a formula to plug in, let's go for it. So we got 3 equals 1.96 times 15 over the square root of n. You think, okay, so we're supposed to solve for square root n. I'll walk you through the steps that I suggest. You might feel comfortable doing it a little bit differently. That's fine with me. Since we have this fraction here, I'm going to create a fraction from the 1.96. I'm going to think of it as 1.96 over 1. And then I'm going to multiply that right side. So to multiply fractions, remember, you take the numerator times the numerator, denominator times denominator. So that would give me 1.96 times 15 is 29.4. And 1 times square root of n is just square root of n. And there's still a 3 over here. At that point, I can multiply this square root of n over to the left. Then I can divide the 3. So I end up with the square root of n equals 9.8. And then how do I get rid of the square root? I can square both sides. The square and the square root cancel out. And 9.8 squared is n equals 96.04. So look at that. We just figured out the sample size. Okay, so you might be thinking, well, you really can't take a sample size of 96.04. That's true. So let's just round it to 96. This researcher should take 96 students in their survey, and that would mean that whatever the average, whatever the sample average is for these 96 students, the researcher is 95% confident that that sample mean is within 3 IQ points of the actual population mean. And you think that's a pretty big survey. That's a lot of students. I'm like, well, okay. But they want 95% confidence that it's within 3. So it makes sense that you might have to take quite a few people in your survey for that. Okay, perfect. Let's stop here. More to come.